No,
especially the young members are really very much encouraged to come to these wonderful series of members colloquia and to the Wednesday math conversations, right? So what should we say about that? That it's just enhances the mood of everybody in the School of Mathematics?
It is not optional. Okay.
No, it is optional. It is optional, but you know, when everybody's happier, everything works much nicer. Okay.
I think I prefer an audience that wants to be here.
Weekly.
Yeah, okay. So without further ado, our first speaker today is Michael Magee. Actually, he cut a portion of the title because it on the website it read Convergence of Unitary Representation and Spectral Gaps of Manifolds. Right?
Right. Okay.
Please.
Thanks for the introduction and the invitation to speak. Okay, so it's a talk about unitary representations of what? So the questions I'm going to talk about today, they make sense for like groups with topology, right? So you could talk about locally compact groups, but today I'm going to talk about discrete groups, so there's going to be no topology. So gamma is going to be a discrete group. And then just to make it even nicer, it's going to be finitely generated. And the good news is we don't actually have to think about very complicated groups to get interesting questions. So I'm just going to give you 3 types of examples, and they're the only ones you need to think about. And even the first example is interesting, and that's free groups. So gamma could be FR, free, non-abelian group, of R generators. And you probably think this is a stupid group, but actually the questions in my talk are already difficult for this group. Okay, but anyway, so we want to be ambitious. So what comes after free groups? Well, for me, it's the fundamental groups of closed orientable surfaces. So I call that gamma G. Pi 1 of a surface, closed oriented surface with G holes. There are G holes. And I call that a surface group. So if you can answer questions about these and then you want to be even more ambitious, then you can talk about hyperbolic free manifold groups. So the last example is gamma sits inside ESL2C. It's discrete and torsion free, and it's such that this acts on hyperbolic free space by extension and Mobius transformations. Is a hyperbolic free manifold. It's a compact hyperbolic free manifold. Okay, and there are much worse types of discrete groups that you can think about, but I'm satisfied with these 3 examples. Okay, so what am I going to talk about? I want to think about all the possible finite dimensional unitary representations of these groups. So I'm going to check a collection of homomorphisms. Gamma UN, where UN is a group of n by n complex unitary matrices. The first general question is, what can you say about this set? Okay, so let me make some comments about it. So if you fix n and try to ask about this set, and in this example, for example, this is a very, very hard question, and people are spending like their whole life working on this. Okay, to say what are the 2-dimensional irreducible representations of a hyperbolic free manifold group? Okay, but I'm not going to fix n. I'm going to let n go to infinity and ask about asymptotic properties of the set. Okay, as a realization. Good. And like I said, the question is, what do we know? Very broad question. What do we know about this? And just one more thing to notice is I'm not talking about equivalence classes of unitary representations right now. I'm talking about I actually know the representation. Okay. So there's one really obvious thing, you know. Every group has trivial representation where you act on the complex numbers by doing nothing. Okay. So you always have a trivial representation where the group does nothing on a line. And then you also have, like, this is just something stupid, but you also have amplification of truth. Right? So you always have n-dimensional representations, but not very interesting. Nothing. So what can you say beyond this? Well, there's a certain nice class of groups that have like a lot of finite dimensional unitary representations, and there are groups that are called residually finite. So in all these examples I showed you, the group is a subgroup of GLMC. And so by a theorem of Malchev, the group is residually finite. Okay, so that's a nice class of groups. Okay, so the examples before, gamma is residually finite. Okay, what does residually finite mean? It means if I take any non-identity element of the group, I can find a homomorphism from my gamma to a finite group that doesn't kill the element, that lives in this homomorphism. Okay? And actually, by taking products, you can extend this to the fact that for any finite set of non-identity elements in my group, I can find a homomorphism to a finite group that is injective on that set, or it doesn't kill any of them. Okay, so why am I bringing this up in the context of unitary representations? So this gives you many unitary representations of the following form. We map gamma to a permutation group, Sn, and then you take the simplest non-trivial representation of Sn, which I call a standard representation. So Sn, right? How do you think about permutations of n? You can think of them as like bijections of a set, or you can think of them as 0-1 matrices. That gives you a representation of Sn, and it's an n-dimensional representation. It's not irreducible, but once you take away the trivial representation, it is irreducible. So that's this standard representation I'm talking about. So it maps to un-1. And what will happen with these representations if you're really using that gamma is residually finite is that these representations will inject on larger and larger. You can take these representations to inject on sets that exhaust the group, right? So it gives you so let's talk about parameter FD is large, much larger than just finding these things. So this type of representation I told you about that comes from a homomorphism. Yeah, let's give this a name. So this is called phi. This would be called real phi. This whole thing. So this type of unitary representation that you get for a group, it's important not just to say that this is large, but it's also important later in my talk for a more specific reason. So I'm going to call it P. Right. This is a certain type of unitary representation that comes from a homomorphism to a permutation group. Any questions so far?
You don't want to take the heck factor of this open division.
I don't want to take the trivial.
No, but if to a nice representation, you don't want to consider also direct factor.
What does it mean, direct factor?
Something it can fall into a UP times UQ.
Okay. Yeah, so I'm going to make sure that this is one transitive, right? Or
That's
no. Okay. No, later on, this distinction won't matter. I understand what you're asking. So I will explain in a couple of blackboards like why this type of representation is important. Exactly what you're asking will have a meaning. Okay, so this is very broad so far, right? And so there are some very hard questions here. So let me point to two extreme types of behavior that the unitary representations of a group can have. So one type of behavior is that you can have a lot of flexibility in the finite dimensional unitary representations of a group. So flexible behavior. So let's take the simplest example. So if gamma is FR, and we look at how FR to UN. Okay. This set is very easy to describe because FR has no relations between the generators. So you just pick a set of generators of the right size, and then you have to say, where do the generators go? So you're picking R unitary matrices. So this is, after you pick a generating set for FR, this is isomorphic to UN of R. Not only is this set like very nice to describe, but it's so nice that it actually has it's actually a group. Right? That doesn't happen generically, but this is a group, and it's a compact group, and it has a Haar measure. It has a Haar measure. So not only you have so much flexibility, but like you have a nice probability measure on the set that allows you to choose them. I mean, this is the analog of the uniform measure. And one really nice thing about this Haar measure is that even though this isomorphism depended on choosing a generating set for FR, the class of this like the actual law of this measure doesn't depend on this. It's invariant under automorphism. So if I act on this set by automorphisms of FR, this measure is invariant by the action. Okay, so that's very easy, but it's important. This behavior extends to circuit groups. So if gamma is this gamma G I talked about, you choose at least two. Okay, you have to be a bit more careful. So you can still ask about gamma G. I prefer to talk about SUN. It's not really a big distinction, don't worry about it. So this thing here, it's already, okay, so the thing up here, it's UNs R, it's a manifold, right? It has a natural structure of a manifold and so on, right? This thing has some singularities already, okay? So there's a problem. But if you want to deal with these singularities, you can ask to just look at the representations that are irreducible. Okay? And so this actually happens to remove the singularities from this. And actually it does something even better. So there's an action of SUN by conjugation on the target here. And once you go to the irreducible things, going to the irreducible makes that action free modulo the center. So it means that I have an action of PSU that I can divide by. But not only can I divide by it, I started with a manifold and I still have a manifold after I divide. So this is a manifold, and even better, this is a symplectic manifold. It has a symplectic form. Like I should say non-degenerate or something, but you know what I mean. It has a symplectic form. That's not a trivial thing. That's the result of a TM ball. Okay, a TM ball. Describe the form and prove that it's closed. And Goldman extended this construction to more general targets. So I'll talk about Goldman as well. It has a symplectic form. It's not a closed manifold, it's an open manifold, but it has a symplectic form, so it has a volume form that comes from topmost power of symplectic form. And what you can do with that is you can try to normalize it to get a probability measure like we had before. Okay. But then you need a theorem, which is that you need to know that this manifold with this volume form is finite mass, right? So that's a theorem. So actually, Witten wrote down a formula for its volume. Witten formula for a finite volume. It's not rigorous, but it was made rigorous by Sengupta. So once you have finite volume, you divide by that, and then you have a probability measure. So that's what I call the Atiyah-Goldman probability measure on that space of representations. I know this is getting like hard, but you can take this as a black box. So this thing is really, you should think of it as the analog of the Haar measure here. But it's invariant under nothing cluster and so on. It's a grand generalization of the Guy-Peterson measure on moduli space of curves.
What the reason you switch from UN to SUN?
Because I wanted to say like, because I wrote a paper about it and I used SUN in my paper, and then I didn't want to think about it more when I wrote my book.
Because the previous things to know that it does not depend on the generator. You use the explicit generators for automorphism group.
Yeah, it's the first one. I don't know another proof. Great. Okay, so there you have like a manifold of representations in every dimension. You have like a nice probability measure. By the way, this probability measure is in the Lebesgue class and so on, right? So it's a nice measure. Okay, that's flexible behavior. What is rigid behavior? What types of rigid representations? So if you take gamma to be SLDZ, D is at least 3, then this there's a very different picture for what can happen. So it's easy to show every row in gamma check D has finite image. It really is quite easy to prove this. But once you know that, you can combine it with something like more high-powered, which is the congruent subgroup property for SLDZ. So congruent subgroup property says that every finite index subgroup of SLDZ is a congruent subgroup, which means it contains principal congruent subgroup of level n, which is the kernel of reduction modulo n. So it's saying every finite index subgroup of SLD comes from congruences. And let me say what this means. So and then the congruent subgroup property of Bass, Milner, and Serre says that then row factors. So it arises in the following way. You first map SLDZ, the SLD Z modulo NZ, and then you pick some representation of this finite group. Okay. For some n and n. The first map is modulo n reduction. Right. So every finite dimensional unitary representation comes from basically number theory.
We know more, right? We know even about the number of n-dimensional unitary representation, given the like exponential in squared or something. It just comes from the fact that these groups have they are expanded. There's a bound on the number of different irreducible representation for each dimension.
Right. Makes sense. I'm sure this can be made effective. Okay, so yeah, in particular, they can't be deformed. They can't be deformed in an equivalent class. All right, so there are two extremes, I guess. And I said we're going to look at asymptotic properties of unitary representations when there are like enough of them. But to do that, we want to be able to compare them to something. And the thing we want to compare them to is not finite dimensional. So I have to tell you about one infinite dimensional representation. So this is the regular representation. So every discrete group has this representation. So it's called lambda gamma, and it maps gamma to the unitary operators on L2. So gamma acts on a function on gamma by translation. So lambda gamma, f, x. This is a unitary representation, preserves square integrable functions. So actually I accepted this for a long time, that this is the right thing to think about. This, why do you always compare to this guy? Okay, so this turns out to be the right thing. And it has a very special property, this representation, I learned recently. So what's special about this representation? It absorbs every unitary representation when you tensor product with that unitary representation. Right, so if I take this unitary representation, and I take a tensor with another unitary representation, I just still get something which is equivalent to this. And it's actually the unique representation that does this. Okay, so I'm just trying to say it's a special representation. And so when you have this infinite dimensional representation, what you want to actually come up with is something which behaves a bit like a trace. Okay, but it's infinite dimensions, so you can't actually take the trace of a matrix. So what you do instead is you take a matrix coefficient. You pick a cyclic vector for the representation, which in this case is the delta function, identity. And you take the matrix coefficient of the diagonal matrix coefficient of that. Let's call that tau of gamma. And this is a complicated way of writing something very simple. This is 1 if gamma is the identity, and 0 else. But what I want to tell you is that this linear functional and this representation, they're really the same object. So you can actually go from this to this by something called the GNS construction. It's not really that important, but it's just sort of like this thing is canonically attached to this. That's all I want you to have in your mind. Okay, I'm doing a lot of setup of the theorems are coming. I still have the blackboard. Okay, before I start telling you theorems, I'm going to tell you why representations that come from permutations are interesting. So the reason is monodromy. So let me explain this in a simple example where I have my gamma is the fundamental group of the surface. And it acts on the hyperbolic plane by isometries, and the quotient is a compact hyperbolic surface. That means a compact surface with a Riemannian metric of constant curvature -1. Okay. So here's X. I want to think about covering spaces of X. Okay, so topological covering spaces or Riemannian covering spaces. If I put a Riemannian structure here, I can talk about Riemannian covering spaces. What is a cover of X, or what is the, if I put a point here on X and I have a degree n cover of X, and I look over this point, I have n points, right, in the fiber. And I can label them one day. It's not really very important. Okay, so this is the fiber of a covering space of X. So what I can do now is, given any loop in X like this, I can follow this fiber along this path as I move on the bottom, right? Then I move along the fibers. I come back. So this is some gamma. I come back, but when I come back, I may have permuted the points in the fiber. This is parallel transport, monodromy. So I get a bijection from the fiber to itself. Let's call that phi of gamma. And it's not very hard to check that phi descends to a homomorphism from the fundamental group of X, or in other words, homomorphism from gamma G to the permutation group. So I get a phi in the form gamma Sn. And this correspondence is actually 1-to-1. If I say that I have a labeling of a fiber. So I can start with a phi in form gamma Sn and back to construct a covering space of X. So I could actually call my covering space X phi, and I'm going to do that. So this is the 1-to-1 correspondence. Okay, so yeah, so this is the reason for me caring about these representations of the form P, because they tell you something about covering spaces of manifolds. Any questions so far? So let's start talking about convergence of unitary representations. Start with weaker notions of convergence and get to stronger ones. I should say a few more things about this. So, yeah, keep talking about probability measures. I haven't used them yet, but like if I said gamma is finitely generated, right? All my gammas are finitely generated. So the same thing as before. I mean, I have to choose where each of the finite generators go to in Sn, and they may have to satisfy a relation, but I have at most that number of choices for each of the generator choosing freely. So it's clear that this is finite. And it gives me a probability measure, which is a uniform probability measure, where I choose everything with the same probability. Okay, so the same setup as I used to draw my pictures on that board. Let's say X is gamma mod H2 is a compact hyperbolic surface. Now consider the random, yeah, let's say G is at least 2 as well. It has to be at least 2 foot. Let's just say got this. Okay, so let's consider a random pair. So I'm going to take X phi as on the board, and the point in X phi, where phi is in Om, gamma Sn is uniformly random. Okay, so just write uniform. Told you how to choose it uniformly. And P is also uniform, but it's in X phi. What does that mean? Well, this thing here has a Riemannian volume form and hence a probability measure, and it lifts to something that you can renormalize on X phi, or you could just say that X phi has the structure of a compact hyperbolic surface, so it has a Riemannian volume form, and you can renormalize it to get a probability measure. So P is a uniform point in this surface with respect to that probability measure. This may be this setup might be familiar to people. You'll see why in a minute. Okay, so the theorem is that at any fixed scale, for all r bigger than 0, with probability tending to 1, as n tends to infinity, the ball in X phi of radius r around P is isomorphic to the ball of radius r around some fixed point, let's call it I, in the hyperbolic plane. Okay. So what it's saying is in this random covering surface, this random negatively curved surface, I'm not saying that every ball of radius r is an embedded hyperbolic ball, but most of them are. And the proportion to r tends to 0 as the degree of the covering space goes to infinity. Okay, so this type of convergence has 2 different names actually. So, two ways to think about this type of convergence. One is Benjamini-Schramm. It's exactly Benjamini-Schramm convergence. I stated it exactly as Benjamini-Schramm would said it in their paper. So this says that X phi tend to H2 like in the sense of Benjamini and Schramm. So Benjamini and Schramm introduced this type of convergence in the setting of graphs, right? And later, many people brought this type of convergence into the setting of manifolds. It's obvious how to transport it. But actually, not many people who use this notion of Benjamini-Schramm convergence actually know well. I mean, many people I talk to don't actually know what Benjamini and Schramm prove. So Benjamini and Schramm prove that if you take a sequence of bounded degree planar graphs, and whatever they are, as if the number of vertices tend to infinity, any possible limit in this sense has to have a recurrent random walk. Okay. Yeah, so this is it's good to say where the definition actually comes from. Okay, so that's one way to describe this convergence, but another way to describe it is it's the same thing as saying that if you take any element of the group algebra of gamma, then the expected value of rho phi, the trace of rho phi gamma tends to, as n tends to infinity, how gamma. Now, I could have just said, it should be Z. So, because of linearity, it's efficient to state for z equals 1. Okay, but I stated it like this because it will tell me how to generalize it. So I take all elements of the group ring, take the expected value of the trace of the representation, extend the representation to a representation of the group ring, and then I take the expected value and I want it to tend to, it should be that as well, this value. Okay, but if z is gamma, it says if gamma is not the identity, this tends to 0. Yeah.
I didn't understand what it converts.
Yeah. How was this matrix coefficient? So it's the matrix coefficient from the trace in the regular representation. It's just saying that it decays at all non-identity elements of gamma.
I guess this is sort of trivial if the injectivity radius.
Right, so the injectivity radius, yeah, if the injectivity radius is not going to infinity here, that's actually not true.
Yeah, I was trying to, but it's not quite.
This extends to the spectrum or just the close?
Spectrum will be the stronger.
Yeah.
So this is called weak convergence.
This notion of convergence you are telling me, is it for bounded space?
The top one?
Yes.
I mean, it was originally for finite graphs, but people adapted. So you just sort of like people are making ad hoc adaptations of this definition. You can make a definition.
But here you want bounded space. What is it? Does that matter? Otherwise, I don't see the whole of the baseband, which you put at random also.
Right, okay, so actually people use this definition without putting the base point, but the way Benjamin and Schramm originally stated the thing was for random pointed sets, Okay. And so I just keep this.
I think when it converges to something as simple as hyperbolic space, you can take all these definitions over again. But in their general definition, you converge to something much more complicated. Then you have to be very careful. I think that's
Okay, so yeah, so the Benjamin and Schramm convergence is something geometric, and this is something in analysis. But the nice thing about this is it's clear how to change this if my representation isn't of form P. Okay, it's clear how to generalize this, right? I mean, if I just have rho, not rho phi, then I just write this. Okay, so that's actually.
And you need to remove measure 0 both from the homomorphism and from the points. You know, what are bad examples?
So okay, make a suggestion and I'll try to say this. What do you mean by bad example?
Yeah, you said this whole probability tending to 1. There are some counter examples, maybe, or maybe there are not, maybe it's 451. I'm asking whether the bad guys need to be both from the point side and from the homomorphism side, and maybe what an example looks like.
So is the theorem true if you fix the bound pins?
Yeah, or if you fix the homomorphism, yeah.
should.
Probably it shouldn't be.
Make something which is disconnected and every component is just, but you can take a category and cover where
From the homomorphism side is clear.
The point, yeah,
from the point point of view, yeah. Which points will be bad?
what points are bad?
Yeah.
I mean, there are points where they're short, like you have a loop downstairs. That loop downstairs lifts to a closed loop.
Yes, but perhaps that's all for almost all covering. This will unloop itself.
Almost all covering. I don't understand. I don't understand.
Well, the question is whether
He was saying, is it true that if you drop the second randomization on the base point, just say fix the point to
yeah.
begin with, then it looks like it should still be true, but it's a technical thing.
Okay, yeah, we can lose delay. Okay.
Let him finish.
How do you fix the point though without? Anyway, okay, wait. I don't completely understand. Yeah, so this is called weak convergence. This exact. You can forget that there was a phi that gave rise to rho, and you can just ask it for any sequence of. You don't have to have expected value. You can ask for any sequence of finite dimensional unitary representations that the trace converges to the trace. That's fine. So yeah, so you can ask about the hyperbolic measure on this. Okay, so this lifts to a measure on gamma G SUN. So yeah, this is also true there. So exactly the analogous statements for the hyperbolic method. Well, let's see that. Exactly the same as this. Yeah, I want to say something more about this theorem. I mean, it's like such a basic thing, right? And for finite graphs, it's not very hard for this, but this is not easy theorem. Like, I don't know easy proof. This is not an easy theorem to me anyway. And from feedback I got from other people, it's a hard theorem, and it uses representation theory of the symmetric group, and I think it uses it in a sort of complicated way, and there is some complicated complex words. But okay, I want to say a word about representation theory. So this relies, the only proof I know of this theorem relies on the approach to representation theory of Sn, which was developed by Vershik and Krukov. And I think it's one example where this approach to representation theory of Sn is actually needed. Maybe you can remove it somehow, but I don't think it's natural to do that.
So the equivalence between the geometric form and the analytic form, this is easy, and it's the component.
Yeah, it's a bit unfair that I didn't explain it, but it depends on what you mean by easy, but it's not super hard. You have to understand something about you know, when does a ball look like a ball in H? Well, there shouldn't be like a lift to something closed. There are only finitely many at every scale, and then okay, you have to understand that actually in the standard representation, the trace is related to the number of fixed points of the monodromy, and the fixed points of the monodromy is related to the number of times a loop down here lifts to a closed loop, not something unfolded. So it's not like to see instantly, but it doesn't use anything for it. Okay, so this is what I have to say about weak convergence, and now go to what Avi asked about spectrum. Okay, so there's something more you can ask. So you say that the sequence of rho I, let me use Greek grammar. I want to infinity. Okay, so this is not good terminology, but it's the one we're stuck with. Okay, so we say it converges strongly to the regular representation if, okay, so now I'm going to generalize this. So how am I going to do that? If for any element of the group ring, limit as I tends to infinity, I want to compare rho I of z, lambda gamma of z, like I did here. So if I wanted to get this definition, I would put trace and trace, but I want something stronger, so I put norm. Both sides are the unique norms that make things into C-star algebras, so they're operator norms. This is a much stronger statement to ask for. They have consequence on the spectrum. Obviously the outliers, but even spectrum inside. Okay. And
I mean, the weakest statement implies that almost spectral. Maybe that was not the spectrum.
Yeah, that's right.
okay. Okay, so when you take the spectrum measure, normalize it, then you have convergence, weak convergence with spectral.
Density of states come.
Yeah, so this is weak convergence with spectral measures, and this is no outliers. Like this is exceptional eigenvalues disappear. Okay, I want to make another.
Understand this? You don't mean some difference in absolute value times d0.
No, I mean this is in U of L2 of gamma. And this is in like some finite dimensional matrix algebra.
And you compare norms?
Yeah, you compare norms. I didn't make a typo, right? No, just checking. Is there a typo?
The lambda of Z belongs to the bounded operator. It's a linear combination of unitary, so it's not a unitary. It's a bounded operator.
Ah, sorry, that's good. And for this definition, it's important to take things in the group algebra, not just the group, because if thing in the group, then this is a unitary has norm 1, and this is a unitary has norm 1, so it doesn't have any content. When you take linear combinations of things and you ask that the norm converts, then it's much deeper.
Only a random finite set will give you an expander in this.
Yeah, so even almost Ramanujan fits into this framework. Almost Ramanujan is just about, so this is a good question. So almost Ramanujan is about linear set in the generators, but this is even stronger because it asks for any polynomial in the generators.
I'm still about the intuition. In what sense convergence of a norm should be viewed as a convergence?
It's real numbers.
This is a real number.
Yes, but you just look at the norm and look at something much more complicated.
What's the more complicated thing?
The operator itself and all its eigenvalue.
It's looking only at the top non-trivial eigenvalue.
Yes.
Yeah. But it's actually possible to use this to gain information about, like, say that this operator, right, had like bands of eigenvalues. Like you can still detect convergence of the spectrum in Hausdorff sense to, but you just take different. Like you have a Z that you want to learn about all this spectrum. You're allowed to play the other Z as well. Okay, this is game.
This is spectral radius.
It's selfish way. So it's actually not clear that, like, given a discrete group, even the examples I told you, that this can ever happen. So it's a definition. Say that gamma is purely matricial fields. This is something we inherited. If this could happen. And I want to now tell you two big theorems. Let's call it EMF. So the first one is a result of hyperbolic for Bjornsson. Says that FR is PMF. Okay, and then I want to impress you by telling you this is in the annals. And this is the main theorem. Okay. Okay, we're waiting this one, something important, but yeah. Okay. And also, okay, so it says that you can find a sequence of finite dimensional unitary representations of free groups such that this happens. This is the operator norm and the regular representation. Yeah, so this is 2005. And I introduced this type of representation called P, right? That came from permutations. And I explained why that's important to me because it has something to do with covering spaces. But for some reason, it was also appealing to somebody else to think about exactly representation of this form without having anything about covering spaces, or they just started thinking about it. So this says you can find a sequence of finite dimensional unitary representations where you have this convergence. But what if I want my unitary representation to come from permutations? So that's good. Did someone resolve this question? It's the theorem of Borden, and Collins.
I don't think we're trying to prove it. Friedman's theorem another way. So
yeah, they got something. They got something. They got something that, yeah, that's true. Borden, and Collins, 2019. So there exists rule I, finite dimensional representations. FR Jackson of the form P and rho converging strongly to the regular representation. Let's put it like this. So this proves that uniformly random phi in Hom FR Sn of rho phi strongly convergent in probability. Which means that this convergence holds in probability. So this is a random variable and this convergence holds in probability. Right, so there's all this stuff about convergence of unitary representation. So where do I enter into the story? So there's a whole other story that I'm very interested in, which is about the spectrum of the Laplacian on hyperbolic surfaces. So yeah, so this is part of the area of spectral geometry. And in 2021, my student and I discovered how to use the notion of strong convergence in spectral geometry to prove spectral gap results for manifolds, for hyperbolic surfaces. Okay. And so what we proved is, this is my student will hide. Okay. So I have to explain some things, but let's say the X is gamma on H2 is a finite area non-compact hyperbolic surface. So gamma is actually a free group in this case. Okay, so such a surface has a metric, so it has a Laplace-Beltrami operator, and this Laplace-Beltrami operator is non-negative. It has spectrum, it has 0, and it has some discrete stuff, and then it has some continuous spectrum. I'm not going to go into detail about this. Spectrum is discrete between 0 and 1/4, and then we definitely have a continuous spectrum. Okay, so you can perform the same construction here to construct covering spaces of X. So let's suppose, to make things simple, that the first non-zero eigenvalue of the Laplacian on X is at least 1/4, which is the infimum, the spectrum of the Laplacian on H2. This is just to make the theorem easier to state. Then a uniformly random, if phi in Hom gamma Sn is uniformly random, lambda 1 of corresponding x phi is at least 1/4 minus small o of 1, with probability tending to 1 as n tends to infinity. I have quite a lot to say about this theorem. This theorem, okay, I should say that 1/4 is optimal. So what to say about this? So this is, okay, so first of all, let me give some motivation. So you have a hyperbolic surface and you look at the first non-zero eigenvalue of the Laplacian. Okay, it's part of differential geometry, but it also tells you a lot of things about the surface. It tells you how combinatorially connected the surface is by Cheeger inequality. It tells you the rate of mixing of the geodesic flow on the surface. It tells you how to do lattice point count on the surface. It tells you the error terms if you want to count geodesics on the surface. I just want to say that it's a very important quantity, okay, and it's a subject of a lot of work. There's a very famous conjecture in number theory called Selberg's Eigenvalue conjecture that says if you take the sequence of covering spaces of H mod SL2Z that come from congruent subgroups, if you take H mod gamma n, that lambda 1 is at least 1/4. So Selberg's Eigenvalue conjecture predicts the existence of such surfaces without the small O1, but it's still open. But I think this is how people expect this conjecture. We expected this to be resolved. Okay, so it would be a consequence of. Okay, so what I want to say about this is that the existence. So this is a probabilistic statement, but even the existence part of this theorem is new. So the existence part of this would also follow from Selberg's conjecture without the small O1. So this is related to something else, which was that it was a conjecture from the 80s of Boozer, whether for compact hyperbolic surfaces, this could happen. Okay. So it was a conjecture of Boozer from the 1980s, whether for compact hyperbolic surfaces, you could have a series of surfaces with genus tending to infinity, and with this type of lower bound on lambda 1. This theorem actually resolves that conjecture by compactification arguments, where you can take something which is finite area non-compact, and compactify it, and only lose a small O1 in the spectral gap. So it also resolves that conjecture.
When we speak of small O of 1, what is variable?
As n tends to infinity. So as n tends to infinity, this thing is tending to 0 and the probability is tending to 1. So actually, the proof of this theorem is quite a general thing that tells you if you have strongly convergent representations of gamma, which are of the form P, then you can transfer the notion of strong convergence to asymptotically optimal spectral gap. So it doesn't. So it uses Borden-Collins. This is the input. So it's a way of taking this and transferring it to something about manifolds. So next.
No, an explicit generators which achieve it.
What's that?
You know that most sets of generators achieve it, but you know explicit ones that do.
Yeah, that's good. Well, there's de-randomization, I guess. This one?
It's not the answer, it's a question, de-randomization.
Yeah, okay.
How do you do it?
You're the one who does.
Can you remind me where the continuous spectrum begins?
At a quarter. Right, so you can start here with X to be arithmetic. Yeah. Then every covering space will be arithmetic. But if you compactify, this compactification procedure loses the fact that that the covering is arithmetic. So what you really want to be able to say is that you could actually start with a compact X here, and then find a sequence of covering spaces where you have this. But there are covering spaces of something compact, so you can start with something compact arithmetic, and then you have a sequence of compact arithmetic surfaces. This holds. So this is possible. So if X is compact, there exists a sequence covering spaces. Let's again say that lambda 1 of X. Covering spaces Xn of X with lambda 1 with of degree n tend to infinity. Lambda 1 of Xn at least 1/4 minus 1. So this uses a new result, which is that surface groups are PMF, pure metristic fields, i.e. there exists a sequence of strongly convergent representations of a surface group. It strongly converges to the regular representation. And in fact, you need something stronger, that they're pure metristic field, but by representations of this particular form. So this is a result of Neuder and myself. Now it's clear, like hopefully now it's clear, at least if you're not exactly following the details, that knowing this operator theoretic property of this group leads to examples of sequences of manifolds with extremal spectral properties. And that gives an impetus to try to establish the existence of strongly convergent finite dimensional unitary representations for other types of groups. So it's just, okay, so it's next theorem is that if X is a hyperbolic three manifold, is compact, then gamma is PMF. What it says is, given any compact hyperbolic three manifold, you can find a series of unitary representations of its fundamental group. That's that when you look at certain vector bundles over the manifolds, the vector bundle has degree tending to infinity. The spectrum of the Laplacian associated with this vector bundle becomes asymptotically optimal. The reason it's a vector bundle and not a covering space is we don't have this P. Let me just finish with one last result. So I keep proving more and more things have this approximation property. Where does it end? So yeah, so I guess it's the last theorem, which is proved here. And the theorem is the SL4Z is null PMF. We cannot prove it for SL3. Open. Okay, we don't know the answer. I should say there are some other questions. Like so, yeah. So we can prove something about. I want to make some open questions. I have like 2 or 3 minutes. So this is about compact hyperbolic three manifolds. So let's make an open question. So the analog of theorem 4 is a conjecture. That we made. Look, it's a very nice question. I give you compact hyperbolic three manifold. Can you find a series of covering spaces? Let's say it's λ1 is at least 1. Can you find a series of covering spaces degree tending to infinity of the compact hyperbolic three manifold where λ1 becomes asymptotically optimal? We don't know. Okay, yeah. So I think that's an open question. I think I'm going to stop here. Thanks for your attention.
Questions?
Yeah.
Mentioned that in theorem 3, even existence is not obvious. I wonder if you consider the analytical graphs of Marcus Pillman's Rivastava by iterative discovering an existence of words.
Yeah, I tried for like several years.
Many people, that's certainly, but you know, the fact that they can't do bipartite may be related to it.
Yeah, but
It's
you
really
may,
No, it's failed
Yeah,
so far.
okay.
People have tried. It's probably
Okay.
true. You take any hyperbolic surface or genus G that's got 2 to the G covers, double covers, and at least one of them is good. And then you iterate that. The analog of Bilou.
You don't need to try. I tested bilineal on my computer as well, and it looks true.
Yeah.
But here's the thing. So you don't need to do. You can do their last paper as well, right? You can try their last.
Yeah.
And also try this.
Yeah.
So it's a very nice open question. So Selberg would actually Selberg would actually tell you that you could remove, like in terms of existence, you can remove small O1. But that's for a very specific family of surfaces, like they come from number theory. Without that constraint, can you prove there exists a sequence of, like, for example, compact hyperbolic surfaces, genus tending to infinity, and lambda 1 at least 1 quarter? These would be the analog of Ramanujan graphs, but for surfaces. This is a great question.
And what Avi was saying was that I used to say you would never do this without a number theory until these Srivastava, Marcus, and Spielman came along and gave this proof of this conjecture we're doing, and he might apply it, which he says definitely apply that to him, and we all believe it. But the thing that's missing there is the Lee-Yang theorem. How to average over all the covers. The Lee-Yang theorem is the Lee-Haleman theorem is a key input in that proof, and that's one of the things that's missing. The basic part, I think, is fine.
Yes.
So the strong convergence is stronger than just the almost Ramanujan property, as you said. So in the same way, do you get something stronger by taking other differential operators than the Laplacian and convergence of the whole spectrum rather than just the bottom part?
Yeah, that's true. So you get something, this is weaker than Selberg because of the O1, but it's stronger in another way. So I could take any, for example, I could take any line bundle over my base, and for every covering space, I could pull up that line bundle, and I could twist by the line bundle at every level, and I would still be able to get this small O1. And then Selberg cannot be that, as far as I know. The line bundle may have nothing to do with number theory.
Some do, some don't.
Okay, if there are no other questions, thanks.